In this video, we'll discuss various different activation functions used in deep learning and also see which of them are typically used as output activation functions. Let's dive right in. Activation functions for deep learning. Let's get started by looking at some traditional activation functions. The first one we already, of course, talked about, the standard logistic function that we also used in logistic regression. As I mentioned, this is a squashing nonlinearity, taking the entire input range and mapping it to an output range from 0 to 1. A quite related activation function is the logistic hyperbolic tangent function, tanh. This is also a squashing nonlinearity, and it takes the entire input range and maps it to the output range -1 to 1. This is not quite as useful for the output layer if you want to, for example, map probabilities that should be between 0 and 1, but for an activation function for the hidden layers, it's actually quite useful because it gives you activations between -1 and 1, symmetric around 0, which tends to work better than having all activations be positive. And that's what would happen if you used logistic activation functions in a hidden layer. Now, another activation function that's actually really simple is the linear activation function, also known as the identity mapping. This is frequently used for regression in the output activation. It is not a squashing nonlinearity, so it takes the entire input range and maps it to the entire output range. And this is actually desirable for regression because you typically don't want to constrain your output to lie within a certain range. Now, a very popular activation function is the so-called rectified linear unit activation function, ReLU. So for inputs below 0, this is actually just exactly 0. And for inputs above 0, it's actually the linear activation function. So this is a piecewise linear function with two linear pieces. And you might actually worry that this is not differentiable, and that's true. At 0, technically, the derivative is not defined. Is it the one from the left function or from the right function? And it turns out that in practice, this doesn't actually matter. In your code, you simply say that, for example, inputs greater equal 0, you use the derivative of the right function, and inputs smaller 0, you use the derivative from the left function. So this piecewise differentiability, that's actually all that we need in order to compute gradients for stochastic gradient descent in practice. So this ReLU activation, that actually has some very convenient properties. For inputs larger than 0, the gradient is simply a constant 1. And that is helpful to avoid the phenomenon of exploding or vanishing gradients that we will see later on. So this makes the ReLU much more robust than, for example, the tanh function. And in fact, the ReLU is the most widely used activation function in deep learning these days. One problem of the ReLU, however, is that of a dying ReLU. So for inputs smaller than 0, a ReLU unit is simply off. And because the gradient is also 0 in that range, there's also no more learning going on. One type of activation function that fixes that problem is the parametric ReLU, the PReLU. For positive inputs, this is exactly the same as a ReLU. But for negative inputs, it is not just 0, rather there is still some slope there. And in fact, the steepness of this slope, alpha, that's a learnable parameter of this activation function. Another type of activation function that fixes the dying ReLU problem is the so-called exponential linear unit, the LU. Again, for positive inputs, this is exactly like the ReLU or like the linear activation. But for negative inputs, this actually saturates to a value of minus alpha. So in this case here, minus 1, with alpha being 1. And the gradient here is actually never quite 0. So there is this saturation to minus alpha, but the gradient doesn't get exactly 0, so there's still learning going on. Another somewhat less well-known activation function is the Gaussian error linear unit, GALU. For large positive inputs, its slope is actually very close to 1, very similar to the ReLU, but not exactly. And for negative inputs, it actually converges to 0. Again, very much like the ReLU, but not without a dip for inputs that are just smaller than 0 by a bit. So this non-monotonicity actually appears somewhat strange, but the original paper introducing the GALU actually stated this to be an advantage. And it also stated it to be an advantage that there is curvature at every point and the gradients are never quite exactly a constant. So there is still learning going on at each point in the input range. Now, an activation function that actually looks quite similar to this GALU is the so-called swish activation function. This activation function was actually discovered by an automated search over different types of activation functions, using similar techniques as we will learn about later on in the course in the lectures on hyperparameter optimization and neural architecture search. The swish activation function also has this same non-monotonicity, and it's not like the authors aimed for this to happen. This is simply what came out of their optimization process as the best activation function for their problems. And indeed, this swish activation function often leads to better results than the ReLU and is becoming very popular these days. So now that we've seen all kinds of different activation functions, let's talk about which activation function to use in the output layer. The choice for this typically depends on the task. For a regression task, I already mentioned that you would typically have output neurons with a linear activation function. And for binary classification, what you would typically want is a logistic function in order to express your predictions as probabilities, just like in logistic regression. In some cases, you could also formulate binary classification as the negative class being -1 and the positive class being +1. And in those cases, the TANH activation can make a lot of sense in order to constrain the outputs to be somewhere between -1 and 1. But typically, you use a logistic activation for binary classification. And then for multi-class classification, if you have k classes, what you typically do is you have k output neurons, and then you compute a softmax distribution over the different pre-activations of these k output neurons. So the probability of my prediction being that yk is 1 is just a softmax over the individual pre-activations. So that is, you can write that as e to the power of pre-activation at output neuron k divided by e to the pre-activation of all the different output activations. And so this was just the prediction of the output being the kth class. And so for the complete output layer, you can write this in a concise matrix vector notation like this. All right, so there's also a natural pairing between the output activation function that you use and the loss function. And for binary classification, we already saw that the cross entropy error is a very natural loss function for the binary classification with a logistic. And for a linear output, we typically use a squared error function like this. And for multi-class classification, one typically uses a generalization of the cross entropy error. It looks like this. And so here, if we actually have k classes, then we write it as a sum. And if k was 2, then, well, we could plug this in here and we would get a function that looks pretty much exactly like this one, except that, well, here we then have predictions for the class 1 and for the class 2, whereas here we only have predictions for the 1 class, and here we just say 1 minus a prediction. But here we would just have a prediction for 1 and for 2, and those would have to sum to 1. But that's really the only difference in these notations. Okay, so this brings us to the end of this video. And as always, I'd like to leave you with some questions to think about for yourself. So thank you, and I'll see you in the next video.